This is the laboratory where we make the isotopic measurements to reconstruct ancient temperatures. So I'm going to show you the different mass spectrometers we use and how we can actually take calcium carbonate samples and end up measuring the composition of carbon-12, carbon-13, or oxygen-18 and oxygen-16. Here's the mass spectrometer we use for measuring the isotopic composition of calcium carbonate we use for paleotemperature reconstruction. Now it all starts here. This is a carousel that is under vacuum because we can't let atmosphere get inside. And we load the carousel up with little capsules filled with calcium carbonate powder. This could be little foraminifera shells, or it could be tiny ground up pieces of limestone, or various other bits of calcium carbonate from geologic samples. One at a time, the computer advances the carousel and the capsules drop into this vat down here. This is a glass vessel filled with phosphoric acid. What happens in the acid is the calcium carbonate reacts with the acid, it fizzes and ultimately produces carbon dioxide, which comes off of here along with a little bit of water from that reaction with the acid. This is a trap. There's a tube here that goes through a vat of alcohol that's sitting at about minus 80 degrees Celsius. Minus 80 degrees is cold enough to take all the water and freeze it to the walls of the stainless steel tube, but it's not cold enough to trap the CO2. So the CO2 gets through, but the water stays behind. And then ultimately, the carbon dioxide is frozen over here in a little finger, a little protrusion that's cooled down to liquid nitrogen temperatures, which is about minus 190 degrees Celsius. That's what's happening right now. There's liquid nitrogen flowing through this cold finger and cooling it down while it traps the carbonate sample. After the CO2 is transferred over here, the valves behind it are closed, the cold finger is warmed up, and then the carbon dioxide is emitted over here, and this is the main part of the instrument. This is the mass spectrometer. The mass spectrometer starts here with what we call the source. The CO2 comes in through this tube right here, and the source is where the gas is ionized. What this means is that there's a filament that emits electrons, and the electrons are bombarded into the carbon dioxide molecules, and they knock off electrons. When that happens, the carbon dioxide becomes a charged particle. It becomes a CO2 plus ion, and it finds itself in a very strong electric field. So it shoots out of this source at very high speeds into the flight tube, which you can see right here. This is the flight tube that's flat here. It's all under very high vacuum. The CO2 ions are all mixed together, all the different masses of CO2. But when they encounter this electromagnet, they actually start to bend. And the amount they bend depends on their mass. So the heavier ones that have the heavier isotopes bend less and are actually take an outside path around this curve, whereas the lighter ones that just have carbon-12 and oxygen-16, they actually take the shorter path, they bend the most and take the inside route. And this here is what's called the collector. And these are different cups at the end that essentially count the arrival of the ions and then communicate that back to the computer. So there's 3 collectors here, one for mass 44, one for mass 45 in the middle, and one for mass 46 on the outside. Mass 44 would be for a carbon-12 and 2 oxygen-16s. Mass 45 would be carbon-13 and 2 oxygen-16s, or alternatively, a carbon-12 and oxygen-17 and an oxygen-16. And then finally, mass 48 would be a carbon-12 and an oxygen-18 and an oxygen-16. And so by counting these 3 different ion beams, we can actually measure the ratio of carbon-13 to 12 and oxygen-18 to 16 in the sample. Here's another mass spectrometer. It's actually a little bit larger than the other one. We use this for some specialized measurements where we don't just measure mass 44, 45, and 46 for carbon dioxide. We actually measure unusual combinations of isotopes, like mass 47 and mass 48. Mass 47 would be, for example, if you had a carbon-13 and an oxygen-18 on the same CO2 molecule. Here's another tool that we use a lot in the laboratory. In this case, it's not for measuring the isotopic composition of calcium carbonate, but it's actually measuring the isotopic composition of organic carbon. It's what we call a CHN analyzer. And what we do is we can put samples in this carousel right here, and they drop in to the machine, And it's basically a column furnace. Gets very hot and introduces the sample to a stream of oxygen. The oxygen combusts the sample and turns organic carbon into carbon dioxide, which is then flushed into the mass spectrometer and ultimately measured. We can actually use this instrument not just for organic carbon, but actually measuring organic nitrogen as well. So we can measure the ratio of nitrogen 15 to nitrogen 14 in the nitrogen that's part of organic molecules as well, like amino acids. But we use this very commonly for measuring the C13 to C12 ratio in organic carbon. If we go back to the Vostok CO2 record and Delta O18 record, what we see is a very strong connection between the temperature in Antarctica and the carbon dioxide in the atmosphere. One can imagine a set of positive feedbacks that take these relatively subtle changes in the Earth's orbit, give rise to the very large climate changes we observe. You can think about this a little bit like the amplifier in a stereo system. The amplifier just takes the signal it's given from the device, whether it's an iPad or an iPod or your phone, and ultimately amplifies it through a speaker so you can hear it. That's a little bit the way the climate system works. Imagine the world today if the obliquity started to change so that we had slightly reduced obliquity and slightly less seasonality. What that would do is it would actually make the wintertime a little less cold, but it would still be plenty cold for snow up in the high northern latitudes. The summertime would be a little cooler as well. It would be a little less warm, and that would mean that the ice and snow that accumulated up in high northern latitudes might actually survive the summer months, and ultimately then that would build up a little bit more. Now, of course, if you started to build up a permanent ice sheet up there, that would have a positive feedback because it would actually reflect more sunlight back to space and cool the planet. Now, what does that do to the carbon dioxide? Well, we know that as the Earth cools, the ocean will cool, and colder seawater will actually hold more carbon dioxide. So we would expect the carbon dioxide to go down a little bit. That will, of course, reinforce the effect of the ice and cool the planet a little bit more, and ultimately then the ice will build up a little bit more. And so on. There are a number of other positive feedbacks, including the height of the ice sheet. So, for example, as the ice accumulates over North America and it builds up larger and larger as carbon dioxide in the atmosphere drops and the ice sheets get bigger and bigger, the ice sheet gets higher in altitude. And as you go up in the atmosphere, it gets colder, and that actually increases the staying power of the ice sheet. So there's another positive feedback associated with building up tall ice sheets that ultimately reach up higher in the atmosphere to colder temperatures. Ultimately, we think these positive feedbacks give rise to these amplification of the ice age cycles so that you build up large ice sheets. There's still a mystery about exactly why they crash completely at the end of these ice age cycles. What you see is these ice age cycles aren't exactly symmetric. You see both in the Vostok record and also in the sediment core record that, in fact, the cooling down of the Earth occurs relatively slowly, and then the warming up actually occurs quite abruptly. So as you move into an ice age, the temperature drops relatively slowly in cycles, and then every now and then you have a large resetting back to a full interglacial. So it's often called a sawtooth pattern because of its asymmetry. One possible explanation for this may be that when you build up a really large ice sheet over North America, eventually the ice sheet is big enough so that it actually starts to melt underneath because the geothermal heat coming from the Earth is so insulated by the size of the ice sheet that it starts to melt at its base. And once it melts at its base, this causes the ice sheet to slump a little bit and lower in elevation. And then when the obliquity cycle changes and you start to melt the ice sheet a little bit, you start to reset it all together, because now at with a wet base, it will actually completely collapse and melt back to the beginning, and you have to start all over again. That may be one of the explanations for this funny sawtooth pattern we see. Until very recently, scientists used to think that the precession of the equinoxes, the roughly 20,000 year period, was the most powerful, because if you looked at 65 degrees north on July 1st, the peak of the summer,
what you saw was that it was the precession of the equinoxes that had the most power on that date. If you actually looked, the 20,000-year cycle was really the strongest. Second was obliquity, and eccentricity was relatively small. If you look at the actual shape of the ice ages, for example, in the sediment records, what you see is something quite different. What you see is that actually over the last 4 or 5 cycles, it looks like a 100,000-year cycle appears to be a lot stronger. And prior to about 600,000 or 700,000 years ago, there's a transition to a much higher frequency of variations. It turns out that prior to about 600,000 or 700,000 years, that it was really the obliquity cycle that appears to be most dominant. And that's always been a bit of a mystery. If Milankovitch was right that the summertime insolation at 65 degrees north was the most important thing for building up an ice sheet, because we care about having cold summer temperatures, then why do we see mostly the obliquity cycle earlier in time? And why do we see such strength of the 100,000-year cycle when eccentricity is the actual weakest of those 3 orbital variations? Well, a colleague of mine, Peter Hybers, actually gave us the answer for the earlier question about the obliquity cycle earlier in the record. Turns out that there's a very simple answer here that actually explains why precession may be a lot less important than we thought. Most of the scientists who followed Milankovitch and thought about how these orbital changes actually led to these ice ages and the cycle of the Pleistocene ice ages, thought about it as Milankovitch did, looking at 65 degrees north on July 1st and looking at how the solar radiation at that time varied through geologic time. But what Peter Hybers reminded us of is the point that actually what the ice sheets care about is probably not the peak summer temperature on July 1st, but the entire energy received over the entire season. What matters is colder season on average. Whether July 1st is particularly warmer or colder may be actually less important. And that's something interesting about the precession of the equinoxes. Think of the situation today where we have the Earth being further from the sun in the summertime, when its northern hemisphere is pointed towards the sun, and closer to the sun in the wintertime. If it weren't for the buildup of anthropogenic greenhouse gases, today would be a wonderful time to build up an ice sheet. In the summertime, the Earth is furthest from the sun, even though the northern hemisphere is pointing towards the sun, and that means we have relatively cool summers and relatively warm winters. It turns out, though, that even though the peak summer is actually cooler today and the peak winter is warmer, because of the elliptical orbit, the Earth spends a little bit more time on the longer side of that ellipse and a little bit shorter time on the short side of the ellipse. That means that even though summers are a little bit cooler, they're also a little bit longer today. And though winters are a little bit warmer, they're actually a little bit shorter today than they would have been 10,000 years ago. 10,000 years ago, it would have been the opposite. We would have had warmer peak summers because the summertime would be closest to the sun on the short end of the ellipse, but they wouldn't have lasted as long. And the wintertime, even though they would be colder, they would have lasted much longer. So, in fact, the precession of the equinoxes, when you average them over the seasonal cycle, actually are probably less important. That doesn't mean that precession has no effect on the climate, just the opposite. Certain types of phenomena really care about the peak warmth in the summer. For example, the monsoons appear to be very sensitive to precession because they care about the peak heating of the land relative to the ocean, and therefore that the precession of the equinoxes really matters. But if you look at the overall buildup or decay of ice sheets over ice age cycles, Peter Hybers explained that it was the obliquity cycle that should be the most important, and indeed that's what we see in the geologic record. As far as the mystery of the 100,000-year cycle, there's still a lot of debate about that. We don't completely understand why that is, but one idea is that this 100,000-year cycle isn't actually a 100,000-year cycle. It's really a combination of obliquity cycles at either 80 or 120,000 years, and just reflects the ultimate buildup over obliquity cycles of large ice sheets and then decay once you create a threshold that melts at the base and ultimately causes that ice sheet to go away. This is an active area of research, and it's still one of the great mysteries of exactly why do you transition from these higher frequency 40,000-year periods to a lower frequency 100,000-year period. It may have something to do with the nature of the ice sheet over North America, that before about 600,000 or 700,000 years ago, the ice sheets were a little bit smaller and they just grew and then decayed every time there was an obliquity change. But something changed around 600,000 or 700,000 years ago, and scientists are still working to figure out exactly what that was. So what can we learn from the Pleistocene about the climate change that's occurring today? What lessons are there from the fluctuation in the Earth's climate, the great ice ages, that might tell us something about the risks we face in the future? Well, one of the lessons that we can see right away is that the Earth is capable of relatively large changes in climate with relatively subtle changes in forcing. Think about the fact that these Milankovitch orbital changes are relatively small. They change only how sunlight is distributed on the Earth, but not how much total energy the Earth receives. And yet they give rise to these enormous ice ages. That's because there are these positive feedbacks, both the ice albedo and the carbon dioxide, that appear to give rise to very large temperature changes and very large changes in the physical climate of the Earth. Another important lesson has to do with the sensitivity of the Earth's climate to carbon dioxide. Now, it wouldn't be fair to blame the entire 5-degree temperature change on carbon dioxide. As we said, the ice albedo feedback is also probably a very important factor. But think about it this way. The changes that we see in Vostok between the interglacials and the glacial maxima are only about 100 parts per million, or going from 180 parts per million to about 280 parts per million. That's an increase in about 50% from a glacial maxima of 180 up to about 280. That's about a 50% increase in carbon dioxide concentration. We, relative to the pre-industrial level, have already achieved roughly a 50% increase, and we're heading for much, much more. Now, if the equilibrium temperature over long time scales, if we just think of the effect of the carbon dioxide, and we use roughly 40% of the glacial interglacial change, or about 2 degrees as a metric, we would suggest that we've already committed the Earth to about a 2-degree warming, and as we go higher, we'll see even more warming than that. Of course, we can't forget the role of ice itself. Ice sheets are not as important as they were during the glacial maximum because they're not nearly as extensive. We just have an ice sheet over Antarctica and over the high northern latitudes on the sea ice in the Arctic, and then, of course, over Greenland. But still, one of the things we anticipate as warming proceeds is those ice sheets will begin to retreat, and we will see the ice albedo feedback in reverse, the snow and ice beginning to melt, leading to a decrease in the Earth's albedo and an amplified warming. And so, in fact, the warming from CO2 may, in fact, be amplified by the ice albedo feedback going forward. One other lesson from the Pleistocene ice ages actually comes from ice cores not from Antarctica but from Greenland. Again, there are a number of different ice cores from Greenland that have been taken over the years, and what you see in these ice cores is a very different picture than the ice cores from Antarctica. Remember that the Greenland ice cores have much higher accumulation rates, and so the resolution is much higher, and also you see a lot more variability than you do in Antarctica. When you look at the Greenland ice cores, and this shows a Greenland ice core record over the last 60,000 years. Over the last 10,000 years, that's a period called the Holocene, and you see quite a bit of variability, but a relatively stable climate in Greenland. This is based on the delta O18 of the ice, in the same way that we used the isotopic composition of the ice in Antarctica to reconstruct the temperature. But as you go back in time, during the glacial period, when we had these large ice sheets over North America and over Northern Europe, what you see is a much more unstable climate. What you see are these large fluctuations we call Dansgaard-Oeschger events after the great polar scientists Willy Dansgaard and Hans Oeschger. These Dansgaard-Oeschger events show up as abrupt warmings that occurred over just a decade or two, and the temperatures in Greenland rose as high as 10 or 15 degrees. This was generally followed by a slow cooling trend that could last a century or perhaps even several millennia in some cases, quite variable in duration. And then ultimately a very abrupt cooling down to the background levels of the glacial period. And so what you see is these abrupt warmings followed by slow coolings and then abrupt coolings back to the baseline. This happened repeatedly for different durations throughout the glacial period as observed in Greenland. It also appears to have happened during the last deglaciation. As ice around 20,000 years ago started to retreat, we know that sea level was starting to rise. There was something called the Bowling-Allerod event, which looks to me like it was just another Dansgaard-Oshkosh event that happened to occur during the deglaciation as the ice was melting. So you saw this abrupt warming followed by a slow cooling, and that slow cooling people call the Younger Dryas, where in Europe things started to warm up. It looked like you were coming out of the glacial, and all of a sudden the ice age came back. This may not be anything unusual other than another Dansgaard-Oshkosh event that happened to occur during the last ice age. There are a number of different theories for what causes these abrupt climate change events. One idea has to do with changes in the way that the ocean transports heat to the high northern latitudes. Another idea is that it has to do with the ice buildup over the Arctic Ocean and over some of the high latitude oceans surrounding Greenland and Iceland, and that this may actually be related to the breakup of a certain amount of sea ice and ice shelves growing out from the Greenland continent. Scientists are still arguing over exactly what the cause of these fluctuations may be. The important thing, though, is that the climate appears to be capable of rather abrupt swings, at least locally. We don't know whether these Dansgaard-Oshkosh events were truly global events, although we do see impacts in other parts of the world as far away as China in terms of the changes in precipitation. So the important lesson is that the climate system is capable of incredibly large and fast changes, and that we can't just assume that climate change as it proceeds going forward will be nice and smooth. There may be some very big surprises.